So now we are moving to the displacement method of example, right? So you can see the same example we did for the force method. Okay. So here in the displacement method, we do not need the statical indeterminacy. We need kinematic indeterminacy, right? Here, how much is the kinematic indeterminacy? At A, unknown displacements are zero, right? Right. Unknown displacements are zero. Why? We know the x displacement, y displacement, and the rotation are zero. At B, you have this displacement and the rotation, right? At C, you have the displacement in x direction and the rotation, right? The rotation, so altogether 2, right? Together 2. So the total number is 0 plus 2 plus 2 is 4, right? But what happens if it is axially rigid? If it is axially rigid, right? If it is axially rigid, this translation and these translations become 0, right? So that is negligible, right? So this becomes 1, this becomes 1, and your kinematic indeterminacy becomes 2. Similar as the statical indeterminacy, right? So that means we need to determine these two displacements. So we are adhering to this assumption, right? So in that case, I will leave you to this, right? So here I'm going to, so this is the original structure with W load, and this is 2L, and here you have VB, and here you have VC, and here you have VA, and here you have MA. So similarly, I would take clockwise rotations and moments are positive, and the upward deflection and upward forces are positive. Okay, this is my sign convention, right? So here I'm going to find this displacement at B. So the deflected profile would look like this. So let me draw it in red color. So here fixed, so no rotation or no displacement. And here you would have some deflection like this. And here you have something, right? So if you draw a tangent, so this is, and this would be theta B, let's say. This is theta C, let's say. Okay, so if you find theta B, it's totally completely equal to this theta, right? So these are the same angle, right? So here it is theta C, and so what I'm going to do is I'm restraining this theta. So that would be, so there are only two displacements. Why? Kinematic indeterminacy is 2, right? Then these two are the unknowns. If it is axially rigid, these translations are negligible, right? So I'm applying, so I'm restraining these displacements. I'm bringing them down to 0. That's what I'm doing. If I'm fixed here, theta b is 0. If I fixed here, theta c is 0, right? So here I'm fixing it, and here I'm fixing it. Okay, so this would be my primary structure, and I'm applying those two displacements. So in the primary structure, you have the loading. So here you don't need any loading. So the third structure, so in here, I'm restraining this theta b and theta c. How? I'm applying a fixed support. So that means theta b is now 0. Theta c is now 0, right? Okay. So what I'm going to do is, now here you have this one, since this is a fixed end, so you know the fixed end moments, right? This is minus w L square. So I will tell that in this way. Oh God. So this was my original structure, right? So you have a deflected shape as I shown you earlier. So here theta 0, here will be theta b, and here theta c, right? So in displacement method, we consider the equilibrium, right? Equilibrium of that joints, right? So where we find the theta b and theta c means here should be the redundant displacement, and here should be the second displacement, right? So that means in the force method, we consider the compatibility, the shape at that joint. And most of the time, the original shape was 0, right? There will be no settlement in the supports, right? And even if it's the fixed support condition, right? So here, it's not like that. Here, we consider the equilibrium, right? So for equilibrium, so you need to consider what is corresponds to this displacement. If it is theta, theta corresponds always to the bending moment. If it is delta, the linear displacement, it corresponds to a force, right? Linear force, right? So since theta, you should consider the moment equilibrium at that joint. Since it is theta c, you should consider the moment equilibrium at this joint, right? So we are going to do that. So now I have fixed everything here, right? So that means these theta b and theta c now are 0, right? So in here, you will have, you can determine this, right? So this is MAS, right? The primary structure. So I'll call it. So here, let's try to call it MAR. MAR, because in the first example I used MAS, right? So here I will say VAR, right? Here the total bending moment is MBR, right? here total bending moments is MCR, right? So the total moment is this plus this. So I'm taking everything clockwise because it's clockwise positive for rotation and upward positive for as per my sign convention. And here you can see if now you are solving for displacements, right? So that means at the end you will find theta b and theta c, but you will not find MA, VA, VB, or VC. So that means this will be your actions, right? VC, VB, VA, and MA will be your action. So I will consider this as my first action, this as my second action, this is third, and this is fourth subsequently, right? Third action. So the sign convention is clockwise positive. So this is clockwise I have applied. Okay. So these are upward forces. That's why I have taken upward positive. Okay. So here now, here original structure theta b and theta c are there. I bring them down to 0 by clamping as fixed, right? But now it is no longer remain as the same structure, right? So here I need to, so here will be b, here it will be b, b r, and here it will be VCR, right? And here you can determine, so you need to apply now. So we remove the displacement, we bring it to 0. Now you should give it back one at a time, right? So I'm giving theta b first. So I will give a unit theta. So that means theta is equal to 1. So I'm giving clockwise rotation. Okay, so that means I have to rotate this support. Otherwise, I can't give, because usually theta is 0 at a support. The only possible way, theta is 0 at a fixed support. So only possible way you can do is you apply a moment and support, rotate the support, right? Right. So this is 1. This is 1. Okay. So you apply a unit rotation. In the force method, you apply unit force, and there you got the displacement per a unit force. Here you get the force per a unit displacement. That is become stiffness. That's why you take S coefficients, stiffness coefficients, right? So you apply a unit rotation and take the force corresponding. So that means the bending moment, right? So S1 here. So that will be contributed by this as well, because these two also bending. So here, because if you rotate the support, not only this beam, this beam also get some bending moment. This beam is also have. So the total S is the summation of these two, right? So this will be S2, 1, right? These are for a unit rotation. Please keep in mind, right? So now I need to apply a unit rotation here. Okay, so I would apply it in the clockwise direction, because that's my clockwise is positive. If you rotate this support theta, right, this support would not get rotated, right? But there will be some induced bending moment, right? There will be some induced bending moment. Okay, so here also you apply a unit rotation. That means theta is 1, right? Theta is exactly 1. So now, due to this rotation, this will induce some bending moment. Let's say it is clockwise direction. And here you have some bending moment. So this is the stiffness, force induced per unit displacement. Actually, here the moment induced per unit rotation, right, is 2, 2. The induced moment at second coordinate due to the unit displacement at the second coordinate. Here there will be induced bending moment S1, 2, right? But since this support is not rotated, no induced bending moment will be in this spot, right? So in this case, you need to consider these actions as well simultaneously, right? Here there will be, so I'll call this the action, okay? Action unit. This is the first action coordinate due to the load at 1. This is the second action coordinate due to the load at 1. So here the total at B will be third action coordinate at 1. Here, this is AU 41, right? So here you have AU 1, 2, right? Here it is AU 2, 2, right? Because this is the action coordinate, this is the redundant displacement coordinate, right? So here AU 3, 2, right? Here it will be AU 4, 2. Now these are for a unit rotation. These are for a unit rotation, right? So that means by the actual displacement. So just check the structure. Just check the structure. So what I did was I just apply a rotation here, a unit rotation. Theta is equal to 1. But the original theta is theta B. So that means I need to multiply everything by theta B. Is that right? I need to multiply everything by theta B. Theta B, multiply everything by theta B. Theta B, multiply everything by theta B. Right? Done. So here, what I did was I just apply a unit rotation at where? At C. But the actual displacement is theta C. So that means I need to multiply it by theta C. Everything will be multiplied by theta C. By theta C. Theta C multiplied by theta C. Now it's okay, right? What I did was I bring them down to theta C, bring them theta B and theta C to 0. Then I apply theta B, sorry, unit rotation at each step in 2 steps, right? I have 2 displacement. I have applied one at a time. How? I'm applying a unit rotation. Why? Usually these people have derived these for unit rotations, right? Derive the appendix for unit rotations. Then I can apply what is the force or the bending moment for a unit rotation, unit displacement or a unit force, right? Then I can multiply it by the original displacement or the rotation, right? So usually in the force, when I referring to a force, it can be either force or moment, okay? That is a common meaning in this kind of analysis. And usually when you refer to displacement, it can be linear displacement as well as the rotations. And the linear displacements corresponds to a force, linear force, and the rotations corresponds to a bending moment, right? So now I need to consider the equilibrium of that two joints, right? So this is my, yes, I can consider the equilibrium at P. So at P, okay, at P and at C, right? At B, so if it is a, so the unknown T is a theta. So that means you should consider MB as the equilibrium. But you know, sigma MB at B, sigma MB is 0, right? The total bending moment at this pin joint or any roller, if it is a roller, it is 0, right? So this is a roller, right? Originally this was a roller. So that means MB total bending moment at B, that equilibrium bending moment is 0. And here as well, theta C corresponds to MC, though that means the total MC. So whatever happens, you know the sigma M at a pin joint or a roller is 0. So that means your original structure, right? The equilibrium of theta, sorry, MB, and so you are taking the equilibrium, right? So the bending moments in that case, the total bending moment is 0 from here, right? So it is 0. We know that, right? There's no any external moments applied, right? So because the internal bending moment is same and equal in the opposite signs, right? So that is the total bending moment is becoming 0. Here, bending moment is 0, right? So here, what will be the bending moment total? So that will be MBR, right? The total bending moment. So that will be this plus this, right? And at C, let's call the total bending moment is MCR, right? Now it is fixed and they have some bending moment, right? So now my B joint is okay. I took this, then I took the bending moment about this, right? Once I add these three structures, I should get this one. If this joint is equilibrium, addition of these three structures and addition of B joint in these structures should be in equilibrium. That is the summary of this method, right? So I need to apply, yes, and I have theta B, I need to multiply it by S11, right? So the total S11 should be multiplied by theta B, right? So that is the total bending moment. This is the bending moment per a unit displacement. That's why we call it a stiffness, right? You can take it by F equals Kx. If X is 1, F becomes K. So that means force is stiffness, right? So, and here it's theta B into S11, right? This total bending moment, right? Here it is S12 into theta C plus S12 into theta C, right? So this is the displacement method, right? So in that case, how we are going to do is we consider this C point, right? So here, the total bending moment is 0. And here you have MCR in the first primary structure, and you apply a unit rotation at B, and there will be induced bending moment, right? You have to consider that, and that is for a unit rotation, and what it will be for theta B rotation. So that brings you S 2, 1, and here that will be theta B, right? That will be theta B, and at C, here it's done, and now at C. So we consider this is at B joint for the original structure. This is the primary structure at B. This is the second structure at unit structure at B. So this is the third structure at B. So this is C at the original structure, and this is C at the primary structure, and this is C at the second structure here, and it is third structure C. It will be S22 into theta C, right? So if this S22 is for a unit rotation, that means theta is 1. So it will be that moment into theta C, because theta C is the original displacement. So what we basically doing is, just see, there are redundant two displacements, theta B and theta C. We make them 0 on purpose. Then we apply each at a time, but we apply only a unit displacement. So then we got the outputs and we multiply them back the original values. That's what we do here and here, right? And once these three structures are added together, we get the original back, right? So I can simplify this part a little bit. I can take theta B and theta C out. Right? So in that case, it will be remaining these four coefficients, S11, S12, S21, and S22. So can you see here you have curly brackets, right? And here you have square brackets. Why? So actually, these forces are for a unit displacement. In this case, it is unit rotation. So these are not going to change on your external loading, because these are the things derived for a unit force, unit rotation. In such case, we use square brackets. These are changing, right? So this change on your external loading. So that's why we use curly brackets. So this is the S mean the stiffness. So this part I can write stiffness into displacement. So this is the displacement matrix. Okay, so I can go ahead and write this whole. So the equilibrium was original structure at each joint, that was 0, right? So I'm writing it in one line. So there were two elements, so both of them were 0. That's why I denoting it as a zero matrix. And here you had a force matrix, right? Here you had a force matrix from the primary structure at the equilibrium. So this is the equilibrium. This is displacement method. We are working with equilibrium at each redundant joint. And in the force method, we consider the compatibility, the shape of the structure. So it will be the displacement method into this, sorry, stiffness matrix into displacement matrix, right? So here you can find this, and now we go for the actions as well. So this is our let's call, no, we don't need that. So from this, so you can determine this, you can determine this, you can determine this, and you have to solve for this. Okay, you have to solve for this one, right? Let's call the actions. So now we only find theta b and theta c, right? In the displacement method, we solve for unknown displacement. Force method, we solve for unknown redundance. So since we are solving for unknown displacement, we need to find each and every action. So we have 4 actions: MA, VA, VB, and VC. So I'll call it MA, VA, and VB, and VC, right? Okay, so here, right? So here what I'm going to do, so at here, these were the action and these were the primary structure. At the primary structure, you have these actions, MAB and AR and VCR, right? So these were your actions, MBR and VAR and VBR and VCR, right? So here, now these actions. So these were the AU11, the action unit. The unit actions were for a unit rotation. So that means the actual action will be the AU multiplied by the actual displacement. In here, it is the displacement theta B, right? So I can write this as AU11 into theta B, and here it's AU12 into theta C at here, the bending moment at first action coordinate, right? So it becomes AU21, sorry, AU12 AU12 to theta C. So I can write the same AU21 theta B. It's here. AU21 into theta B plus AU22 into theta C. Right, guys, I can write for each action coordinate, right? AU, this is 22 into theta C. So this is AU 31 into theta B. So here it is AU 32 into theta C. Here it is AU 41 into theta B. And here it is AU 42 into theta C. So you can simplify this part by this, right? So you can take theta B and theta C out. So you will be remaining something like this. AU11 and dot 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 AU41, right? And here AU11, and here the second column AU12 dot dot dot. So that means AU22, AU32, and AU42. This is also an action unit matrix. So that's why I use square brackets. Here I need to find the curly brackets. Why? This is dependent on the external loading. So what is this actually? Theta B and theta C. Again, this corresponds to the displacement matrix we solved earlier, right? So that means this is the action matrix, right? And this is the action of the primary structure. We call it AR. And this I can tell as the action unit matrix. And this is the same displacement matrix. So this would be our first step. And we know this part when we can solve this. Once you solve this, you can plug it here. Then you already have solved this, already know this. You can find this and you can solve for this. So these are the classical analysis method using matrix displacement method. So this is our first equation, and this is our second equation to find the required action and displacement. Actually, we needed two equations to find theta B and theta C. Here there are two equations using the equilibrium. So actually in this equation there are two equations, right? So to find that redundant theta B and theta C, once you find this, it becomes determinate. So then you can easily find using this combined equation, right? So we will move into an example. So we shall solve the same example, right? So here you can see we need to find theta B and theta C, right? So then we need to find MA and MVA, VB and VC, right? So now I'm making this complex structure into 3 simplified versions, right? So can you see this is the second and this is the third, right? From each, this becomes something you can solve, right? So we are going to find the equilibrium at each joint where we consider the redundant displacements, right? Unknown displacements. And here you can see for this, you know, the equilibrium, the total bending moment is 0. The total bending moment about this point is 0. Why? It's not a fixed joint, so it does not restrain any rotations. So once you apply a load, the beam will rotate, right? So that means it cannot restrain it. So there will be no restraint force against the rotation. So that means no bending moment generated, right? There will be some bending moment in either side, but this point is a pin joint and the total bending moment is in equilibrium. It is equal and opposite, right? So I can find at first redundant coordinate of the displacement. Here is the first, here is the second, and I can see the total bending moments are 0. That's not a problem. So here you need to find MBR and VBR. So I'll call this first one, I'll call this second, and I'll call this third. Right? At each step, we need to determine the stiffness and the actions, right? So those are our requirements. So I will go with the first. So the first one was fixed with loading, right? So it is fixed, right? This was our primary structure, and we know if it is W, this was L, and this was L. So the reaction here is W L by 2, right? Here the reaction is from this beam is WL by 2, and reaction from this part is WL by 2. That means the total is WL. Here it will be WL over WL by 2. So this is simple L. This is simple L, and the bending moment. So you know the friction moments, right? So let me show you. So can you, no, it's not here. Can you see? Your ends are fixed, right? So your fixed end moments F1 and F2, you can see it's marked in clockwise direction. So the F2 is minus WL squared over 2L. F2 is plus WL squared over 2L, right? So the shear is WL by 2, right? And you should consider about the sign convention that appendix has used. Our sign convention is clockwise positive and upward positive. It seems this appendix has used the same sign convention as well, right? The clockwise is positive and the upward forces are positive, right? So we are going back to the presentation, and we have to apply a unit rotation in the clockwise direction. Sorry, it's not here, it's not here, it's not here, it's still the primary structure. And we can mark the forces required for the equilibrium, right? At the first coordinate, so the total bending moment, here the total bending moment, right? So MB is contributed by this beam and this beam. So it was plus WL square, OL squared over 2L. From here, it has a minus contribution. For this beam, it had this bending moment, it had something like this, right? So this arrow shows the total of that. Okay. Right. So the total bending moment, you have to separate those and consider, right? Here there will be something like this. Here there will be something like this according to the appendix. So this was negative, this was positive, and this was negative, this was positive, right? So this is the summation of, right, at B. So minus WL squared over 2L. This is plus WL squared over 2L, minus WL squared over 2L, and plus WL squared over 2L. So that means MB is plus WL squared over 2L minus WL squared over 2L. So that brings you to 0. And MC, so this is MBR, right? Actually MBR and MCR. MCR is plus WL squared over 2L, right? So the actions. So here I mark the clockwise always. So the clockwise moment is now there's actually an anti-clockwise bending moment. So that means MAR is equal to minus WL squared over 2L. And VAR equals to WL by 2. And it's positive to our sign convention, according to our sign convention. And VBR, it is WL plus WL, sorry, WL by 2 plus WL by 2. It is WL. This is VCR, and it is WL by 2. Right? So now the first step is done. We found the forces required for the equilibrium and the actions, right? So we go to the second one, right? Here we are going to apply a unit rotation. So this is, since this is a fixed support, we have to rotate this support by applying a theta, right? So this is 1 because we are applying unit rotation. Okay. So if you apply a rotation like this, so your final displacement will be look like this, the beam, right? So since this beam is rotated by some rotation, so this will induce some bending moment in this way. This will be this way, and here it is this way. So how to take this direction? Actually, it's given in the appendix, right? So can you see? So where was it? So here you are giving a unit rotation. At that point, you have 4ei over L squared moment. If it is theta, 4ei theta over L. So at the far end, right, you have induced bending moment due to this rotation. If it is theta, let's call this theta x, then this point bending moment is 4ei theta x over L. And since this due to this theta x, it will have 2ei theta x over L here. That is the bending moment. The rotation is still zero. Only this support is rotated. These are the induced bending moment, right? This F1 and this F2, right, are the forces caused by a unit displacement. The unit displacement was applied only to particular location, right? So this is for EIO. If you apply clockwise, the F1 is all will also be clockwise, right? So F2 will also be in the clockwise direction, right? It's like this. So you can take this direction as the bending moment, and you can see this curved part is, so someone is pushing in this way. So the induced moment is in this way as well. And you can take these reactions as well, since we need the actions. So F3 is plus 6 ei over L squared, and F4 is minus. So how to determine these directions, right? So can you see this one? And so here we are trying to rotate this beam like this, right? So that means it should restrain it in this way to keep the original position back, right? So that means this F4 is negative, right? So we get F4 as minus 6ei over L squared according to our sign convention. So here you have some bending moment like this. So this try to bend this beam like this. That means it should keep the original position. So that means we should push back this point toward here. So that means F3 is positive and 6 ei over L squared. So that is something more logical to determine the direction of the actions, right? So we'll move back to the presentation, and can you see this? So now our MB, so this becomes now S11, right? Because it is actually MB, but we are applying a unit rotation, and that becomes S11, right? One here it should be S21, right? So S11 is this. If this is one unit rotation, so that means 4ei over L, and it is contributed by this as well, plus 4ei over L. So how? This beam and this beam also rotated. So there will be two bending moments in the clockwise direction. That's why this becomes 8ei over L. So your S21, right? S21 for per unit rotation at P becomes, you remember, this is in this direction, this is in this direction. You can check it from the appendix. It will be 2ei. It is in the clockwise, that's why positive. over L. So these are for a unit rotation. Right? You need to multiply them back by the original displacement theta b to consider the equilibrium. You remember? So, but we are solving it in a matrix, right? And here the actions, here will be something, here will be something. So you remember MA. So there is this bending moment, right? So we call it AU 1, 1. So that brings you 2EI over L. So applied unit rotation here, this is 4EI over L. The far end, this is 2EI over L. This is what exactly what's happening in the moment distribution and slope deflection method, right? You apply a theta to a particular point and it carries over half to the remote end. That means the far end, right? If you apply theta somewhere, depending on the support condition, it will carry over half. So that's why if this is 4 EI over L, this becomes 2 EI over L, right? Theta is not here because it is a unit rotation, 1, right? So this action 2, AU21, this is the AU21. This is the summation of this is the AU31. Here it is AU41 and this is AU11. Here it becomes, you remember this, try to bend this, rotate this beam in this way, right? This try to rotate this, think comparatively, right? This try to rotate this beam in this way. So the reaction should be in downward direction. So this brings you minus 6 EI over L. I don't remember, it's L squared. Yes, it's L squared. Doesn't matter, you can check it from the appendix as well. AU31. So this try to bend this beam in this way. So this means this end it try to go down. So this should push it back. So that means it is in the upward direction. And here, if you check this end, this try to rotate this beam like this. So this should push this back. So that means it's in the downward direction. Six EI over L squared. Okay. Okay. So this brings you to 0. U41 is how much? So you can determine it should be, so this try to bend this beam like this bending moment at B, this one. So it should push it back, this end. 6 EI, it is positive over L squared. So it's done, right? So the second step is done. So we find these for a unit displacement. So that means we should multiply them back by the original displacement at theta b. So that means we should multiply it by theta b. Right? That's why we are multiplying everything back this displacement. This is the original displacement matrix. Can you see? This action unit matrix and the stiffness coefficients are multiplied by the displacement matrix. So once you find this, it's just a matter of finding the displacement, right? So we are going to the third step, and here we need to apply a rotation to theta c. So that means only theta c will rotate. So we apply a clockwise rotation of 1. So there will be some induced bending moment, but this support is not rotated. So that means no effect on this beam, right? So no induced bending moments, right? You have to check the actions. Check the actions. And check the actions, right? So if you apply something like this, your S1, 2. So that means it is force at first point due to the unit displacement at the second coordinate, and the force at second coordinate due to the unit displacement at the second coordinate, right? So that is stiffness S, right? So there will be induced bending moment only this part, not in this part. Why? It is 0, right? This support is not rotated. This part is not affected. This remains as it is, right? So it is, if it is 1 here for EI over L, here should be 2 EI over L. S22 should be 4 EI over L. It is from the appendix, right? So we apply unit rotation and check the force. That's called the stiffness, right? So these are the green color ones are the actions you have to find. So the AU, now it's 1 due to the displacement at second coordinate. AU 22, AU 32, and AU 42, right? So AU 12 is this. So no effect on this part, so that brings you to 0. No induced bending moments because this support is not moving or rotating. AU22. So this no loading or no effect on this part. So AU22 is 0. And AU32, right? So if you apply a theta like this, so 32, this part is 0 because no effect from this one. This is 0. But here you have something. If you want this part, just consider how this part is going to rotate the entire beam in this way. So it should bring back to the original location. So that means in the downward direction, 6 EI over L squared. So this is going to rotate in this way. So that means the reaction is, it should bring it back in the original position, and it is 6 EI over L squared. So don't be confused, simple L squared should be everywhere. Right? Yes. So good practice is you take only the magnitude from the appendix and you determine the sign or the direction according to your sign convention. That's good practice, right? So these are the bending moments for a unit unit rotation actually, and these are the actions for a unit rotation. So you need to multiply everything by theta c. Then that's done. The third step is okay, right? And can you see now? Yes, here we need to find the we need to consider the equilibrium at first and second redundant displacement coordinate. So we separate it into three structures, and now we are going to superimpose everything, right? So first we determined this equilibrium at joint B and C. So it is zero, right? At the original structure, bending moments are zero, right? So that is 0 and 0. And here we had how much? The first primary structure. We had 0 and WL squared over 2L. Then the stiffness matrix. So S11 is 8EI over L, 2EI over L, and S22 is 4EI over L. So I can take 2EI over L out. So I can take 2EI over L out, and will be remaining. Here it's 8 was originally 8EI over L, and here 1, and here 2. Right, so we need to find this theta b and theta c. Do not need to worry on the sign because we are solving for that, and since we did adhere to a particular sign convention, it will be positive or negative at the end. So then you can determine the sign of theta c and theta b. So I will remove it to here. So it's becoming 0 minus WL squared over 12. This should be multiplied by the inverse of this. So this is the S, right? Into D. So how to find S inverse? So I should call this a K. Then I plug it into the back to the matrix. So now S is 4K, K, K, and 2K. So I need the determinant. That is simply you multiply the main diagonal and reduce the subdiagonal multiplication. 4K into 2K is 8K squared minus K into K, K squared. It is 7K squared. And the inverse is S inverse. You should interchange these two main diagonal. So that is 2K and this is 4K. You should interchange this. And you multiply the subdiagonal by -1. This is minus K. This is minus K. And you divide it by the determinant. It is 7K squared. So you will be ended up with K will be 1K will be cancelling. So it's 2 minus 1 minus 1, 4. And 7k will be remaining underneath. So 7k is this 14 EI over L. So that means k you bring here, right? 7k EI over L. This is 7k. You divided it by 7k, right? So that means multiply it by 1 over 7k, right? So k is 2 EI over L, 7k is 14 EI over L. So multiply it by L over 14 EI, right? So this is the S inverse, right? So I have to multiply this by S inverse, right? To get D. So D is L over 14 EI. I can take the WL squared over 12. No, I will take it here. That was 2 and 4 minus 1 and minus 1 into, I take the WL squared over 12 out. So the remaining was 0 and this was minus 1. Why? I bring it back to this side, right? You remember 0 and minus WL squared to 12. And yes, we are done. So I can multiply this and this directly. So it will be W into L cube over 12 into 14. How much it is? 12 into 14 means 168 EI. So I need to multiply these matrices, this one and this one. So that means 2 into 0 minus 1 into minus 1. So that brings you 1. Minus 1 into 0. So you multiply each row by column. Each row by column. You take one row and finish every column in this matrix. So there's only one column. And minus 1 into 0 plus 4 into minus 1. It should be minus 4. So your theta B and theta C equals to W L square L cube over 168 EI into 1 and minus 4. This is correct, right? So theta B is positive, right? So that means theta B is actually in the clockwise direction, but theta C is negative. That means it is in actually anti-clockwise direction. So we are correct, right? So we can go ahead and determine the force matrix, sorry, action matrix. So the A was AR plus AU into D. So this we found, right? So AR What was AR? The primary structure, WL squared over 2L, WL by 2, WL by 2. And you see, this is the first primary structure, first step, right? Because now this is the first step, right? The second step, third step. So here is the first step. Here is the first step. This is the simplification of second and third step. So that was minus WL squared over 2L and WL by 2, WL and WL by 2, right? So AU, it is, I can take no, I can't erase those, right? Since I have saved it. So here I can take 6 EI over L squared out. That is common, right? 6 EI L squared over 6 EI over L squared, right? It's simple L. I can take 6 EI over L squared out. So originally there was 2 EI over L. So that brings you, no, you can only take 2 EI over L squared, right? So 2 EI you take out, L squared you take out. So that brings you multiply it by additional L. And the second was minus 6 EI over L squared, right? So that means 3. 6 EI over L squared. The third one was 0. The fourth one was plus 3. Is it correct? Here it is TVI over L squared. So that means you should multiply it by L. So you take it out. It's minus 3. Here it is 0. Here it is plus 3. So here it is 0 and 0. Here it's minus 3 and plus 3. Here it is 0 and 0, minus 3, plus 3. You multiply it by the displacement matrix, WL L cube over 168 EI 1 and minus 4. Right? So you can simplify these terms. So L squared, L remaining, EI cancelled. So 2 cancelled. It's 81, 84. Right? WL over 84 becomes so WL over 84 right into how much? So I have to multiply this by this. L into 1, 0 into 4. So that means L. Right? 3 into 1, 0. Then minus 3. 0 into 1 minus 3 into minus 4 plus 12. 3 into 1 minus 3 into 4, right? So that brings you 3 minus 12, so that means minus 9. Into this matrix. So once you solve this, right, these are the components, and you have to add these two matrices, right? So that's pretty easy. So once you add this, you will get the actions required. So your total actions, the final actions will be, so these things, right? MA, VA, VB, and VC. And if you solve those, you will ended up with, from this one, you will ended up with WL squared over 14, it is minus, and 13 WL over 28, and 8 WL over 7, and 11 WL over 28, right? So this brings you MA is minus, so that means we consider clockwise, so that means MA is actually in anti-clockwise direction, and VA is positive, as VB and VC, so that brings you those are in the positive directions. Okay, thank you very much.